This is Dr. Shankaraiah from Department of Physics. In this presentation, I am going to discuss about question bank on Module 1, which is crystal structure. And I am going to discuss about the part B, that is on long answer question. So this is part B, first part. In the next presentation, I will discuss about the part B, second. So the first question in part B is explain the concepts space lattice, basis, unit cell, and lattice parameter. So we need to discuss about space lattice, and we need to discuss about basis, unit cell, and lattice parameter. So these are all the four different terms which we need to discuss about. Okay, yeah. So first we need to start with space lattice. What is space lattice, right? So space lattice is a three-dimensional network of points, and so here we have given the definition. Space lattice is defined as an array of points in 3 dimensions, in which every point has surroundings identical to every other point. So if you are sitting in a space lattice, at any lattice point you see it and look at the surroundings will be the same. That is why we are saying that every point has surroundings identical to every other point. And this is in 3 dimensions. So space lattice is defined as an array of points in 3 dimensions, in which every point has surroundings identical to every other point. Okay. So space lattice can be generated by successive translations. Okay, starting from an initial point, we can generate space lattice using translation operation. Okay, so yeah, so you start with a simple point. So yeah, so this is all about how to generate this space lattice. Okay, start from an initial point, for example here, and use translation. Okay, translate this point at a distance of, for example, t1 along x-axis. So you are going to generate a point here. Again, use translation in the same direction at a distance of t1. So you are going to generate a point here. Again, after t1, repeat this translation again. You are going to generate a point here. So you are going to generate a row of points along x-axis. Now use similar translation along other direction. Okay, so somewhere it is mentioned. Okay, so yeah, so this is a row of points. If we generate along x-axis, starting from an initial point, we are going to generate row of points along x-axis. Then we are going to start in other axis. So the two axes are not non-collinear. Okay. So we are going to generate the other row of points along y-axis with another translation of t2. Okay. So from every point we are going to generate a row of points in y-axis, right? So from here, so translation of t2, translation of t2. So you are going to generate array of points in 2 dimensions by repeating this translation operation along x and y direction. So this is 2 dimension, right? So if you join these points, you are going to see a 2-dimensional lattice, right? So if this is a translation operation done in 2 dimensions, this is along x and this is along y. Okay, so if we repeat this translation operation even in z direction, along z direction, we are going to generate a space lattice in 3 dimensions, right? So let us see how are we going to generate the space lattice in 3 dimensions. Okay, earlier we have seen a 2-dimensional space lattice. Now we have used the translation operation along 3 axes, right? So this is x and this is y, for example, and this is z. Okay, so by generating this, by using this translation operation along x, we have generated a row of points, and we are using this translation operation along y-axis, and we have generated another row of points, right? So along z-axis, we use the translation to generate another row of points. Okay, when we join these points, we see clearly there is a 3-dimensional network of points, and you see there is a clear lattice. Okay, so this is how we generate the space lattice in 3 dimension using translation, repeated translation operation. So that is about space lattice. So the next one is basis. What is basis? Okay, so a space lattice is a mathematical abstraction. The crystal structure is formed only when a group of atoms is identically attached to each lattice site. So space lattice is nothing but a mathematical abstraction. We are just using the repeated translation operation and we are generating a lattice, but there is no atom sitting on the lattice, so we do not know what it is, right? So to get a physical picture of this, we need to attach a group of atoms to each lattice point on the space lattice. So say space lattice has these lattice sites or lattice points. So if we attach a group of atoms to this space lattice point or lattice site, then only this lattice is going to give us some physical picture. Okay. So the group of atoms that is attached, the group of atoms that is associated with every lattice point is called basis. Right? So without attaching any group or any atom to each lattice point, there is no physical understanding of the lattice. It is just a mathematical abstraction. Now when we attach a group or a single atom or a group of atoms to each lattice point, then we are going to generate a crystal, right, a material. Okay, so the group of atoms or an atom that is associated with each lattice point is called as basis. Okay, and one important property is that the basis must be identical in composition, arrangement and orientation such that the crystal appears exactly same at one point as does it at any other point in the lattice or crystal. Okay, so whatever lattice, whatever atom which we are going to attach to each lattice side, this basis, that is called basis, and that basis must be same, identical in composition, arrangement and orientation, so that wherever you are sitting, you should see the same surroundings at every point, right? So that is why this basis must be identical in composition, orientation and arrangement. Okay. So that is basis. So to get the complete crystal structure, we need to generate a space lattice first and attach a basis to each lattice side. That will give us the complete crystal structure as shown here. So first we have generated the space lattice, right? So this is the space lattice. This is the through two-dimensional space lattice here we have taken, and this is the basis. Here just we have mathematical pattern. So array of points. Now we are attaching a group of atoms. So for example, this is one atom, sodium atom, and this is chlorine atom. So each lattice site we are attaching a group of atoms, and then we will get some NaCl crystal, sodium chloride crystal, or you can attach different points based on what kind of crystal you are going to generate using this lattice and basis. Okay, so lattice plus basis will give us the complete crystal structure. Yeah. Okay, so the next one is unit cell, right? So because of the inherent periodicity, the space lattice can be represented by a unit cell. Okay, we know that lattice has periodicity. I mean, at every point, the distance between any two points is same, right? So A, and B, for example, A. So the distance between any two points is same, and you can generate this point, you can generate this lattice, infinite lattice, by repeating this translation operation. So there is an inherent periodicity in this space lattice. That means the distance between any two points is same, and if by using this translation operation with the same period, you are going to generate the lattice more and more. Infinite space lattice you can generate using this periodicity. Because of this periodicity property of the space lattice, you can represent this lattice by a unit cell. Okay, so unit cell is the smallest geometrical unit which, when repeated in space, indefinitely generate the space lattice. Okay, so because of the inherent periodicity, we are going to use the unit cell. You repeat this unit cell, you generate the unit cell, and you are going to generate, repeat this unit cell, you are going to generate the space lattice. Okay, so the unit cell is the smallest geometrical unit. This is the smallest geometrical unit, and when you repeat the smallest geometrical unit in space, you are going to generate the space lattice. This is possible because the space lattice has this periodicity property. Okay. So hence it is the smallest volume that carries the full description of the entire lattice. If you know the unit cell of a crystal, then you can generate, or you can understand the full description of the lattice. Okay. So this is a unit cell, the smallest geometrical unit cell, and there are three axial lengths here. So for example, the distance between 2 points along along x-axis, maybe alpha. So the distance between along x, yeah. So let me take this as x-axis. Let me take this as y-axis, and let me take this as z-axis. Okay. So the distance between two lattice points along x-axis is A. The distance between two lattice point along y-axis is B. The distance between two lattice point along z-axis is C. Okay. So these A, B, C are called as lattice parameters or lattice constants or axial lengths. Axial lengths. The angle between x and y axis. Angle between x and y axis is gamma. Angle between y and z axis is alpha. Angle between x and z axis is beta. Okay. So combining these axial lengths and interaxial angles, right? Combining the axial lengths ABC and the three interaxial angles alpha, beta, gamma are called as lattice parameters. Lattice parameters are nothing but the axial lengths ABC as well as the interaxial angles alpha, beta, gamma. So these are the lattice parameters or lattice constant. Okay. So we have completed the first question, that is discussing about space lattice, unit cell basis and lattice parameters. So the second question is enlist the 7 crystal systems, draw the diagrams neatly. So first we need to enlist 7 crystal systems and we need to draw these the diagrams. Okay. So the 7 crystal systems. Okay. So the 7 crystal systems are cubic. First one is cubic, tetragonal, cubic, tetragonal, orthorhombic crystal system, monoclinic crystal system, triclinic crystal system, hexagonal crystal system and trigonal or rhombohedral crystal system. So basically there are 7 crystal systems. The 7 crystal systems are cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal and trigonal or rhombohedral. So these are the 7 crystal systems. Next we need to draw these the diagrams. Okay. So let us draw the diagrams neatly. So these 7 crystal systems, we need to draw the diagrams. Okay. So cubic, there are 3 different cubic lattices. Okay. Crystal system. So simple cubic, body center, simple cubic, body center cubic and face center cubic. So this is cubic system and this is tetragonal system. Okay. Tetragonal, you can have 2 different tetragonal lattices and this is orthorhombic. Okay. So cubic crystal, tetragonal crystal and orthorhombic crystal. Right. We need to draw all these diagrams neatly. Okay. And then a monoclinic, triclinic, trigonal and hexagonal. So basically there are 7 crystal systems. So this is 1, cubic is 1, tetragonal is 2, orthorhombic is 3, and then monoclinic is 4, triclinic is 5, trigonal is 6 and hexagonal is 7. So we need to draw all these 7 crystal systems neatly. After enlisting them, we need to draw these crystal system. We can draw one of them. So for example, simple cubic and a simple tetragonal, simple orthorhombic, right? So one of them in each crystal system rather than all these one monoclinic, triclinic, trigonal and hexagonal. So then yeah, so we have completed this second question, 7 crystal systems and then the diagrams. The third question is draw the 14 Bravais lattices. Okay, so we need to draw the 14 Bravais lattices, right? So Bravais lattices have this periodicity or periodic lattices, right? So there are 14 Bravais lattices as mentioned, and these 14 Bravais lattices are grouped into 7 crystal system. So out of them there are primitive unit cells and non-primitive unit cells, right? So these 14 Bravais lattices are grouped into 7 crystal systems, and these 7 crystal systems are cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal and trigonal. Okay, now we have to draw all the 14 Bravais lattices. In the earlier question we can draw only 7 unit lattices, but now we need to draw all the 14 lattices, Bravais lattices. Okay, so first cubic has 3 Bravais lattices, simple cubic, body centered cubic and face centered cubic. Similarly tetragonal has 2. Okay, so tetragonal has 2, so 4, 5 lattices, Bravais lattices, and orthorhombic has 4. So 6, 7, 8, 9 Brebes lattices. So this is orthorhombic. Cubic 3, tetragonal 2 and orthorhombic 4. Okay, so there are 8 Brebes lattices. In only these 3 crystal systems, we have 8 Brebes lattices. Okay. Then monoclinic 2, so 9, 10, 11, 12 and 13. So we have missed somewhere 1. So there are basically 14 Brebes lattices, right? So 3, 5, 9, 10. Yeah. So 3, 5, 9. So these are 9, right? 9, 10, 11, 12, 13, 14. So 14 Brebes lattices. We need to draw all these 14 Brebes lattices. So the next question is define coordination number, packing fraction and obtain the packing fraction of simple cubic lattice. Okay. So coordination number is defined as the number of atoms in a crystal is the number of nearest neighbors. Okay. Coordination number of an atom in a crystal. Take any atom in a crystal and we want to know the coordination number of that atom. Okay. So coordination number of that atom is nothing but the number of nearest neighbors of that atom. Okay. Okay. Understood? We are going to take an atom in the crystal, right? So there are many atoms. We are going to sit at one atom. We are going to sit at this atom and we want to look at the coordination number of this atom. So the coordination number of this atom is nothing but the number of nearest neighbors of this atom. So the number of nearest neighbors of a particular atom is called as the coordination number. Next, atomic packing fraction. So atomic packing fraction is the space occupied by atoms in a unit cell is known as atomic packing fraction. Basically, whatever is the space that is occupied by the atoms is called atomic packing fraction and it is defined as a ratio of volume of effective number of atoms in the unit cell to the total volume of the unit cell. Okay. So Z into mu divided or small v divided by the capital V, where Z is number of atoms per unit cell. So simple cubic unit cell, for example, has 1, Z is equal to 1. So number of atoms per unit cell is 1 for simple cubic. And number of atoms per unit cell, Z is 2 per body center and 4 for face center, right? So Z is number of atoms per unit cell and multiplied by the volume of each atom. So you have some number of atoms per unit cell. So what is the volume of that atoms? And so Z into small v, which is volume of each atom, divided by the volume of the total unit cell. Okay, so this will give us the atomic packing fraction or the volume occupied by the effective number of atoms that are present in a unit cell. Okay, so this is atomic packing fraction as well as coordination number, and they have asked us to calculate the atomic packing fraction for simple cubic unit cell. So for simple cubic unit cell, the number of atoms per unit cell Z is 1. Okay, and the volume of, we are taking spherical atom and the spherical atom, the volume is 4 by 3 pi r cube, where r is the radius of each atom, and total volume of the unit cell is a cube. So a cube is a is nothing but for simple cubic a is equal to 2r. The distance between any two atoms in a simple cubic is a, which is equal to 2r. Okay, so a cube is the volume of simple cubic unit cell and a is nothing but 2r. So 2r cube is 8r cube, and here the volume of each spherical atom is 4 by 3 pi r cube. Okay, so when we calculate this, when we write down this atomic packing fraction, which is Z into volume of each atom divided by the total volume of the unit cell, then what we are getting, 1, Z is 1 and volume of each unit cell is 4 by 3 pi r cube divided by 8 r cube. Okay, so 4 2s are and then 5. Yeah, so r cube will go away. So what we get is 5 by 6 basically. So that 5 by 6 is 0.52%. So 52% of the space is occupied by, so here fraction, but percentage is 52% of the space is occupied by the effective number of atoms in a simple cubic unit cell. Okay. Yeah. So we have defined a coordination number and we have defined atomic packing fraction, and then we have calculated the atomic packing fraction for simple cubic units. So the next question is define atomic packing fraction and obtain the packing fraction of body center cubic units. Okay. So we have defined atomic packing fraction as the space fraction of space occupied by the atoms in a unit cell, and it is the ratio of the effective number of atoms in a unit cell divided by the total volume of the unit cell. Okay, so effective number of atoms is Z into volume of each atom is small v divided by volume of the unit cell. Okay, so this is atomic packing fraction, and we need to calculate the atomic packing fraction for body centered cubic units. So for body centered cubic unit cell, the effective number of atoms or number of atoms per unit cell is 2. Okay, and we know that for body centered cubic unit cell, A is 4r by square root 3, or radius of each atom is square root 3 by 4 into A. So this is the radius of atom in BCC unit cell. Okay, and we know the spherical atom volume is 4 by 3 phi r cube. Okay, and volume of the unit cell is A cube. And from this radius equation, we can calculate A is 4r by square root 3, A cube is 64r cube by 3 root 3. And when we write the equation for atomic packing fraction, Z into small v, volume of each atom divided by the total volume of the unit cell. So that is 2 into 4 by 3 phi r cube divided by 64r cube by 3 root. So what we will get is 5 into root 3 by 8, which is 0.68. So basically, 68% of space is occupied by atoms in BCC unit cell. Okay, so 68% of the space is occupied by the atoms in a BCC unit cell. So atomic packing fraction is 0.68 for body centered cubic units. So we have defined what is atomic packing fraction, and we have calculated the atomic packing fraction for BCC unit cell. Next question. Explain the FCC structure and obtain the packing fraction for face-centered cubic units. Okay. So what is face-centered cubic unit cell? Face-centered cubic unit cell is a non-primitive unit cell having 6 lattice points at the centers of 6 faces and 8 atoms at the corners of a cube. So face-centered cubic unit cell is not a primitive unit cell. Primitive unit cell is the one which has 1 atom per unit cell. Okay, but face-centered unit cell is having Z as 4. The number of atoms per unit cell for FCC is 4, so it is not a primitive cell. It is a non-primitive unit cell, and because there are 8 atoms at the 8 corners of the unit cell, and there are atoms at the each phase, so there are 6 atoms, 6 phases. Okay, so FCC is a non-primitive unit cell because it is having Z as 4. The effective number of atoms per unit cell is 4 for FCC because there are 8 atoms at the 8 corners and 6 atoms at the 6 phases. And the atomic packing fraction for face-centered cubic units. Okay, so we know the definition of atomic packing fraction. So that is given here, Z into V divided by capital V, where Z is number of atoms per unit cell. This V is the volume of atom divided by the volume of unit cell. Okay, so here Z is equal to 4 because FCC, right? So 4 into V by volume is A cube. Okay, so for FCC, the radius of atom is A by 2 root 2. So from this equation, we can write A is actually 2 root 2 into R. Right? So A cube is 2 root 2 into R cube. So that is this. So Z is 4. Volume of each atom is 4 by 3 phi R cube divided by the volume of the unit cell. You are going to get pi by 3 root 2, which is 0.7. So basically, atomic packing fraction is 0.74. Our total percentage is 74% of volume is occupied by atoms in FCC units. So simple cubic unit cell 0.52 or 52%, BCC unit cell 68%, and FCC unit cell is 74% of volume. So it is, as we go from simple to BCC to FCC, it is getting more and more packed, right? So FCC unit cell is a more packed unit cell compared to BCC and simple cubic units. So if they ask any question, show that FCC unit cell is the more closely packed unit cell compared to BCC and simple cubic. We need to calculate the atomic packing fraction for simple cubic. body center cubic and face center cubic, and then we can say that face center cubic has 0.74 or 74% compared to BCC, which is 68%, and a simple cubic, which is 52%. We can say that FCC is the most closely packed unit set. What are Miller indices? Explain the rules for defining Miller indices with an example. Show that planes 100, 110 and 111 planes. First, we need to discuss about Miller indices, and then what are the rules to find out the Miller indices. Then we need to draw these planes. So the position and orientation of a lattice plane in a crystal are determined by three smallest whole numbers, which have the ratio with one another as the reciprocals of the intercept of the plane on the three crystallographic axes. Okay, and these numbers are called as Miller indices. Basically, Miller indices will tell us about the position and orientation of a lattice plane in a crystal. Okay, crystal has many parallel lattice planes, and we can know the position and orientation of each lattice plane using these Miller indices. And what are these Miller indices? Miller indices are basically obtained by the reciprocals of the intercepts. Okay, if we know the intercepts of this plane along XYZ directions, write down the reciprocals, and by using these reciprocals, we can find out these Miller indices, which are smallest whole numbers. These are the smallest whole numbers which have the same ratios with one another as the reciprocals of the intercept of the plane. Okay, so let us see the rules. What are the rules? Basically, Miller indices tell us about the position and orientation of a crystal plane in a crystal, and these are the smallest integers, whole numbers, which have the ratios, which are the same ratios with one another as the reciprocals of the intercepts. And what are the rules to find out these Miller indices? First, to find out the Miller indices, first we need to determine the intercepts along XYZ directions. Determine the intercepts along XYZ directions, the first point. Once we know the intercepts, we express the intercept in terms of base vectors PA, QB or RC. Basically, we write down as P is to Q is to R, as A is to 2B is to 3C. For example, A is along X, 2B is along Y, and 3C is along X. So once we know the intercepts, we are going to write down these intercepts in terms of these base vectors, and then we form the reciprocals of these intercepts. So once we write down them P, Q, R, then we are going to find out the reciprocals 1 by P, 1 by Q, and 1 by R. Okay, so that is the third rule. Then if the reciprocals are fractions, each fraction is multiplied by the least common denominator. If there are fractions, for example, if there are 1 by 2 and 1 by 3 and 1, so then there are fractions we need to take out, or we need to find out this least common denominator and multiply this least common denominator. For example, here the least common denominator is 6. So then 6 we are going to find out here is 3 is 2 is 6. Okay. So after multiplying with if the reciprocals are fractions, each fraction is multiplied by the least common denominator and reduce them to the smallest integer. So 3 to 6 we obtained as the set of integers. Okay. Yeah, so once we obtain these integers, we are going to put them in closed parentheses without commas. Okay. So these integers are called as Miller indices. So we are defining as d by q as d by p as these. D is nothing but the least common denominator which we multiply if there are fractions, right? So d by p as h, d by q as k, and d by r as l. Okay. So we are going to put these integers in parentheses without commas, h, k, l, and these are the integers, Miller indices of the given plane. Okay. So these are the rules to find out the Miller indices of any given plane. First, write down the intercepts along xyz directions. If any plane is parallel to any of the coordinate axes, the intercept is going to be 0. For example, the plane is parallel to x-axis. Given plane is parallel to x-axis. Then intercept along x-axis is infinite because the plane is never going to intercept this x-axis, right? If a plane is parallel to any of the coordinate axes, then the intercept along that coordinate axis has to be taken as infinite. First, write down the intercept. Then take the reciprocals of the intercepts. If there are fractions in reciprocals of these intercepts, multiply with the least common denominator. And then once you get these integers, put these integers in a closed parenthesis without commas. Those are the Miller indices. So these are the planes, 100 plane. So this is 100 plane. Okay. And this is 110 plane. And this is 111 plane. Okay. So these are the three planes that we need to draw. Okay. Yeah. So with this we have completely answered the question. Next question is, obtain the equation for interplanar spacing for orthogonal systems. Calculate the ratio of the planes 100, 110 and 111 planes. Okay. So how to obtain, how to determine, how to derive the equation of interplanar spacing in a crystal system. Okay, so the distance d between successive lattice planes is called as interplanar spacing. So we know that crystal has parallel planes, right? So crystal has parallel planes, and this distance between any two parallel planes is nothing but the interplanar spacing or interplanar distance d. Okay. So the interplanar distance d involves the axial lengths of the unit cell and the Miller indices of the planes. If you know the axial lengths and Miller indices, then we can derive this interplanar distance. And we shall derive an expression for d in case of cubic system only. So we are going to use cubic system and derive this interplanar spacing for cubic system. Okay. So we know that the three axes of a cubic crystal are mutually perpendicular. So that is why they are mentioned as orthogonal system. Orthogonal system means they are perpendicular to the axes, are perpendicular to each other. Okay. So let ABC be one family of parallel. So this ABC, this is one of the parallel plane I am taking. To draw the interplanar spacing, I need one more plane, for example. So this is that one more plane. There is one more plane, but which I didn't show. Okay. So this is one plane and this is another plane. The distance between these two planes is actually the interplanar spacing d. Okay. So the distance between these two parallel planes is interplanar spacing. I need to derive the equation for this interplanar spacing. Okay. So first I have considered this plane ABC, which is a parallel, which is one in from the parallel set. Let its Miller indices be A by H, B by K and C by L. So these are the Miller indices of the plane ABC. Okay, so A by H is along x-axis, B by K is along y-axis and C by L is along z-axis. So these are the Miller indices. These are the intercepts along x, y, z directions. So the next plane of the parallel, the set parallel to ABC passes to the origin of the coordinate axis. Yeah, so that I have not shown. Yeah, so this is the next parallel plane. Yeah, so this is the plane. So this is another plane. So I need to find out the distance between these two planes. Okay. So therefore, ON is the length of the normal from the origin to the plane is equal to D. Okay. So if I draw a normal to this plane ABC, so that is this ON. So ON. So ON is actually the normal to the plane ABC, and that is actually the distance, interplanar distance between these two planes. Okay. Let alpha, beta, gamma be the angles ON makes with the three crystallographic axes. So if I draw this normal, okay, let me erase all these. Okay, so I have the normal to this plane ABC. This is the normal, and this normal is ON. So this normal is making angles with ABC, x, y, z directions. So with x-axis it is making an angle of alpha, with y-axis it is making an angle of beta, with z-axis it is making an angle of gamma. Okay, so alpha, beta, gamma. So these are the angles that are made by this normal ON with the crystallographic axis x, y, z. Okay. So then I can write down this directional cosines. Okay, so using for alpha I can use this triangle. Okay, so this is the triangle I am going to use, right? So for this, yeah, so this is ON. So for this I want to write cos alpha. So cos alpha is adjacent by opposite. So adjacent is ON. So ON is adjacent and hypotenuse is OA. Okay, so ON I know that is D, interplanar spacing D, and OA. So OA is A by H. Okay. So from this, similarly, I can write cos beta. Okay, so for cos beta, I can use another triangle, right? So I want beta. So this is y-axis. So this is y-axis. So this is beta. So right. Okay. So for this this triangle OBN, adjacent is ON divided by OB is the hypotenuse. So the D by B by K. Similarly, the other the angle gamma along z axis. So for along z axis, I am going to take this triangle. So that is adjacent is ON. Okay, sorry. So I need to take yeah. So ON is making an angle, right? So ON. So ON is the adjacent and hypotenuse is OC. Okay. So ON is D and OC is C by F. So now we have written the direction cosines of these normal making angle along using this normal making angle alpha, beta, gamma along x, y, z directions. And then we know the direction, sum of the direction cosines of a line must be equal to unity. So that means cos square alpha, cos square beta plus cos square gamma must be equal to 1. So using that, we got this equation d square by a square by h square plus d square by b square by k square plus d square by c square by l square. So this is cos square alpha square, cos square beta square plus cos square gamma square must be equal to 1. So d square I have taken it out common. So h square by a square, k square by b square, l square by c square, which is equal to 1. And then d is equal d is equal to 1 by square root of all these terms. So that I am taking it as to numerator. So I am writing it as minus 1 by 2. If I take cubic system, for a cubic system, A is equal to B is equal to C. Okay. So then A is equal to B is equal to C. So then what I'll get is D is equal to A by square root h square plus k square plus l square. Okay. So this is what I got. So this is the interplanar's distance, the derivation of the interplanar distance. Okay. The next question, write a short note on lattice parameter, derive an expression for lattice parameter based on density of the atom, volume of the atom. First we need to write what is a lattice parameter. Then we need to derive expression for lattice parameter using density. So lattice parameters is nothing but axial length as well as interaxial angles. So ABC are the axial lengths and alpha, beta, gamma are the interaxial angles. So we can draw a unit cell and show them. For example, like here, one can draw a unit cell and show that so one can draw this unit cell and you can show A, B, C and alpha, beta, gamma, so that these are the lattice parameters. We can draw this unit cell, and once we draw this unit cell, so both the axial lengths ABC as well as interaxial angles alpha, beta, gamma are known as basic lattice parameters. And then we need to derive equation for lattice parameter using the density. Okay, so first we are going to derive density, and then using the density equation we are going to calculate the lattice parameter, right? So as a unit cell possesses all the structural properties of a bulk crystal, the density of a unit cell must be the same as that bulk crystal. That is right. So if you know the unit cell, then unit cell properties then that are the same as the bulk crystal, because unit cell is the smallest geometrical unit. You repeat this unit cell in space, you are going to generate the crystal. Okay, so the density definition is mass per volume. Okay, so I am defining mass per volume. Mass is Z into W divided by V. Okay, so what is this W? W is the effective number of atoms per unit cell. Z is the effective number of atoms per unit cell, and W is the mass of each atom, which is given by M by Ne. Okay, so how do I find out the mass of each atom? Okay, so mass of each atom is found out by M, which is molecular weight of the material. So I have given the material which is having some molecular weight. From that I am going to find out the mass of each atom. Okay, so that is why I am writing the mass of each atom W as M by Na, where M is molecular weight divided by Avogadro number. Na is the Avogadro number. So total molecular weight divided by the Avogadro number will give me the mass of each atom. So that is W. Effective number of your atoms per unit cell into mass of the atom divided by the volume of the unit cell. That will give me the density. Right? So density rho is equal to Z into M. W is actually M by Na. So Z into M by Na into V. Right? And so now once I have this density, where Z is number of atoms per unit cell, M is molecular weight, Na is Avogadro number, and V is volume of the unit cell. Now, for a simple cubic unit cell, for example, I know simple cubic, okay, let me not write. So let me use this equation. Rho is equal to Z into M by Na into V is volume of any cubic unit cell. Volume of any cubic unit cell is A cube. So Na into A cube. So this is density. From this density, I want the lattice parameter A cube. Okay. So A cube will be Z into M divided by Na into rho. Or you can write the equation for A. So A is equal to Z into M divided by Na, which is Avogadro number, into rho power 1 by 3. So this is the lattice parameter A in terms of density and volume of the units. Z into M divided by Na into rho power 1 by 3. Right? So we have derived the lattice parameter using density and volume. Okay. So we have replaced volume by A cube, and then from the A cube we have written the equation for A, lattice constant, in terms of density. Okay. So we have defined the lattice parameter, and then we have derived the equation for lattice constant or lattice parameter in terms of density using volume of the units. Okay. So that completes the answer to this question. Next question, define the packing density, obtain the packing fractions of simple cubic, body center cubic and face center cubic unit cells. Okay. So we have defined atomic packing fraction many times. So fraction of space occupied by atoms in a unit cell is defined as atomic packing fraction, and you can define it in terms of atomic packing fraction definition mathematically. Z into V divided by capital V, where Z is number of atoms per unit cell, V is volume of each atom in a unit cell, and this V is the volume of units. Okay, so for a simple cubic unit cell, Z is equal to 1, and volume of each atom is A cube, so that is 8R cube, and spherical atom volume is 4 by 3 pi R cube. So we are going to get the atomic packing fraction as 5 by 6, which is 0.52. For BCC, same formula, right? So for all the unit cells, the atomic packing fraction formula is same, Z into volume of each atom divided by volume of the unit cell. Okay. So if you know the so here for BCC we are going to use the radius of each atom, where radius of each atom is square root 3 by 4 into A. So from that we get A, and then we substitute in A cube, and we get we write this formula Z into V by V. So that is 0.68 for BCC. Next is FCC. FCC, the radius of atoms for FCC is A by 2 root 2, or A is equal to R into 2 root. Okay. So by substituting this formula, a atomic packing fraction is defined as Z into small v divided by volume of each unit cell. Right. So Z is number of atoms per unit cell. For FCC, Z is equal to 4. Volume of each atom is 4 by 3 pi R cube, and volume of the unit cell is A cube. So from this we get A, which is R into 2R, 2 root 2. So A cube, substituting this in the atomic packing fraction formula, we get 74, 0.7. Okay. So we successfully answered all these points in the question: packing density and atomic packing fraction for simple cubic, body centered cubic and face centered cubic units. So these are some of the textbooks and references which I have used in this presentation. And finally, to summarize, in this presentation I have discussed the answers to 10 questions in part B, long answer questions. And in the next presentation I will discuss the remaining 10 long answer questions of part. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.